Welcome to the fascinating world of printing. Today we explore a specific type, flexographic printing. It's more common than you might think. From food packaging to newspapers, it's everywhere. This method is versatile and efficient. Join me as we unravel the intricacies of flexographic printing. Flexographic printing uses flexible relief plates. These plates transfer ink onto various materials. This process creates the images and text we see. It's a vital part of our consumer landscape. Understanding flexography means appreciating its impact on our daily lives.
The story of flexography begins in the late 19th century, a time of great innovation and industrial growth. Early forms of this printing method utilized rubber printing plates, which were quite revolutionary at the time. These rubber plates were inked and then pressed onto various surfaces, allowing for the transfer of images and text. Initially, this method was known as aniline printing, named after the aniline dyes used in the inks. The inks, derived from coal tar dyes, were known for their vibrant colors but also had a strong, often unpleasant odor. This strong odor led to concerns about the toxicity of the inks, which in turn limited the applications of aniline printing to non-food packaging. Over time, the technology behind flexographic printing evolved significantly. Innovations in materials and processes helped to address the early limitations. By the 1950s, the name of the process was changed to flexographic printing, reflecting the advancements and broader acceptance of the technology. One of the major advancements was the introduction of flexible photopolymer plates, which replaced the older rubber plates. These new plates offered higher quality prints and greater durability, making the process more efficient and reliable. Alongside the development of better plates, the inks used in flexographic printing also improved. They became less toxic and more environmentally friendly. These advancements broadened the applications of flexographic printing, allowing it to be used for a wide range of products from food packaging to labels and beyond. Today, flexographic printing is a versatile and widely used printing method, known for its efficiency and high-quality results.
Flexographic printing is incredibly versatile. It's used in a wide range of industries. Packaging is a major application. Think of food wrappers, cardboard boxes, and shopping bags. All often use flexography. This printing method is ideal for large quantities. Beyond packaging, flexography has other uses. It's used in printing newspapers, magazines, and catalogs. The labels on many products are also printed this way. Even envelopes and corrugated cardboard boxes utilize this technology. Its adaptability makes it a crucial part of the printing industry.
Like all technology, flexography has seen innovations. One significant development is digital plate making. This process eliminates the need for film negatives. It results in faster production times and higher quality. Another innovation is the use of water-based inks. These are more environmentally friendly than solvent-based inks. The printing presses themselves have also improved. Modern presses are faster and more precise. They can handle larger printing runs and more complex designs. These innovations have increased efficiency. They also enhance the quality and sustainability of flexographic printing.
Section 5. The environmental price of printing. While essential, flexographic printing has environmental impacts. Traditional inks contain volatile organic compounds, or VOCs. These can pollute the air during the printing process. The disposal of printing plates and leftover inks also presents a challenge. These materials can contribute to landfill waste. The manufacturing of printing plates requires energy and resources. This process can generate greenhouse gases. The transportation of materials, from inks to finished products, also adds to the carbon footprint. It's crucial to acknowledge these impacts. We must find ways to make flexographic printing more sustainable.
Section 6. Sustainability in flexographic printing. In recent years, the flexographic printing industry has made significant strides towards adopting more sustainable practices. This shift is driven by a growing awareness of environmental issues and a commitment to reducing the industry's ecological footprint. The industry recognizes the need for sustainability. Professionals across the sector are actively engaging in discussions and collaborations to identify and implement best practices that promote environmental stewardship. Efforts are underway to minimize the environmental impact of flexography. This includes optimizing printing processes to reduce energy consumption and emissions, as well as adopting new technologies that are more environmentally friendly. One focus is on developing and using eco-friendly inks. These inks are designed to have a lower environmental impact, both in terms of their production and their use in the printing process. Water-based inks are becoming increasingly popular. They offer a viable alternative to traditional solvent-based inks, which are known for their high levels of volatile organic compounds, VOCs. Water-based inks release fewer VOCs and are easier to recycle. This not only helps to improve air quality, but also makes the recycling process more efficient and less harmful to the environment. Another initiative is reducing waste. By implementing more efficient production techniques and better waste management practices, the industry is working to minimize the amount of waste generated during the printing process. Printing companies are implementing recycling programs. These programs aim to recycle as much material as possible, from paper and cardboard to printing plates and ink containers. They are also exploring ways to reuse printing plates. Reusing plates not only reduces waste, but also lowers the cost of production, making it a win-win for both the environment and the industry. Some are transitioning to digital plate making, which eliminates the need for chemical processing and film waste. Digital plate making is a more sustainable option as it reduces the use of harmful chemicals and generates less waste. These efforts are steps in the right direction. The industry is continuously seeking new ways to improve its sustainability practices and reduce its environmental impact. They demonstrate a commitment to environmentally responsible printing. By adopting these sustainable practices, the flexographic printing industry is paving the way for a greener future, ensuring that printing can be both effective and environmentally friendly.
Section 7. The future of flexographic printing. Looking ahead, the future of flexographic printing seems bright. The demand for packaging and printed materials is unlikely to diminish. The industry's focus on sustainability will drive further innovation. We can expect to see even more eco-friendly inks and printing processes. Digital printing technologies will likely play a larger role in flexography. This will allow for shorter print runs and personalized designs. The integration of automation and robotics will further enhance efficiency. Flexographic printing will continue to evolve. It will remain a vital part of our manufacturing and consumer landscape. Section 8. Conclusion. Flexographic printing has come a long way since its inception. From its humble beginnings with rudimentary rubber plates, it has evolved into a sophisticated and versatile printing method. Over the decades, the technology has seen significant advancements, adapting to the changing needs of the industry and the demands of consumers. From early rubber plates to sophisticated digital systems, it has continually adapted. The introduction of digital flexographic printing systems has revolutionized the industry, offering greater precision, efficiency, and flexibility. These advancements have enabled printers to produce high-quality prints at a faster rate, meeting the growing demand for customized and short-run printing. This method brings us the packaging, labels, and printed materials we use daily. Flexographic printing is used in a wide range of applications, from food packaging and beverage labels to pharmaceutical packaging and household products. Its versatility and ability to print on various substrates make it an indispensable part of our daily lives. We've explored the environmental challenges and the industry's response. The flexographic printing industry faces several environmental challenges, including the use of non-renewable resources, waste generation, and the emission of volatile organic compounds, VOCs. However, the industry has been proactive in addressing these issues through innovation and sustainable practices. Efforts to minimize waste and utilize eco-friendly materials are encouraging. Companies are increasingly adopting eco-friendly inks, recyclable substrates, and energy-efficient printing processes. These efforts not only reduce the environmental impact, but also align with the growing consumer demand for sustainable products. As consumers, we can play our part. By making informed choices and supporting brands that prioritize sustainability, we can drive positive change in the industry. Our purchasing decisions have the power to influence the market and encourage more companies to adopt environmentally responsible practices. Choosing products with sustainable packaging is a step. Opting for products with eco-friendly packaging, such as those made from recycled materials or designed for recyclability, can significantly reduce our environmental footprint. Every small action counts in the larger effort to protect our planet. Supporting companies committed to environmentally responsible printing is crucial. By endorsing businesses that invest in sustainable technologies and practices, we can help create a more sustainable future. These companies are leading the way in reducing the environmental impact of flexographic printing and setting new standards for the industry. Together, we can ensure that flexographic printing continues to meet our needs. The future of flexographic printing looks promising, with ongoing advancements in technology and a growing emphasis on sustainability. By working together, the industry, consumers, and policymakers can create a more sustainable and efficient printing ecosystem. We can do so while minimizing its impact on the planet. Through continued innovation, responsible practices, and conscious consumer choices, we can ensure that flexographic printing remains a vital and sustainable part of our world. Let us all contribute to a greener future by supporting and promoting environmentally responsible flexographic printing. Section 9, Glossary of Terms. Flexography, a printing method using flexible relief plates to transfer ink onto various materials. Photopolymer plates, light-sensitive plates used in flexographic printing to create the printing image. VOCs, or volatile organic compounds, chemicals that can evaporate at room temperature and contribute to air pollution. Water-based inks, inks that use water as the primary solvent, making them more environmentally friendly than solvent-based inks. Digital plate making, a process of creating printing plates directly from digital files, eliminating the need for film negatives.
Our planet groans under the weight of human progress, a burden that grows heavier with each passing day. Industries, while vital for our modern lives and economic growth, leave behind a trail of waste that is often overlooked. This waste pollutes our air, water, and land, disrupting delicate ecosystems and threatening biodiversity. We must urgently find ways to mitigate this impact to preserve our environment for future generations. One pressing issue is the disposal of industrial waste, particularly from the printing industry, which generates significant amounts of waste. Waste ink, a byproduct of printing processes, poses a significant environmental hazard due to its toxic components. Traditional disposal methods often involve incineration or landfill, both of which contribute to air and water pollution, exacerbating the problem. These practices release harmful toxins into the environment, endangering both human health and wildlife and causing long-term damage. The need for sustainable solutions for waste ink management is more critical than ever, as we strive to reduce our environmental footprint and protect our planet. Flexographic printing, widely used for packaging, faces a mounting waste ink problem. This method, while efficient, generates significant amounts of ink that often end up polluting the environment. The inks used in flexographic printing contain pigments and solvents that can contaminate water sources and harm aquatic life. The industry's reliance on traditional disposal methods further exacerbates the problem. Incineration, while a common disposal method, releases harmful pollutants into the atmosphere, contributing to air pollution and climate change. Landfill disposal, on the other hand, risks leaching these harmful substances into the soil and groundwater, posing long-term environmental risks. The search for sustainable and environmentally friendly solutions to address this challenge is paramount. In the realm of scientific innovation, a team of dedicated researchers is tackling this challenge head-on. Dr. Saber Ibrahim, Dr. Hager Fahmy, and Dr. Salah Lotfy have joined forces to develop a groundbreaking solution for waste ink management. Their combined expertise and relentless pursuit of excellence have led to significant advancements in this field.
Our collaborative efforts focus on the synthesis of a novel tri-copolymer, PEI-PGMA-PEGDA, using gamma irradiation. This innovative material has unique properties that make it highly effective in capturing and neutralizing waste ink. This offers a promising avenue for sustainable waste management in the flexographic printing industry. By integrating this tri-copolymer into existing processes, we can significantly reduce the environmental footprint of printing operations.
This innovative approach not only addresses the environmental concerns associated with waste ink, such as pollution and hazardous waste, but also paves the way for a more sustainable future for the printing industry. It encourages the adoption of eco-friendly practices and technologies that benefit both the industry and the planet.
Our work embodies the spirit of scientific inquiry, pushing the boundaries of what is possible, driven by a commitment to finding practical solutions to pressing global challenges. We believe that through innovation and collaboration, we can make a meaningful impact on the world.
At the heart of this groundbreaking research lies a unique tri-copolymer, PEI-PGMA-PEGDA. This complex molecule, with its long chain-like structure, holds the key to trapping and neutralizing the harmful components found in waste ink. Imagine a microscopic net, specifically designed to capture and hold on to the pigments and solvents that make waste ink so harmful. This tri-copolymer acts as that net, effectively removing these pollutants from the environment. Its intricate structure is the result of meticulous design and synthesis, a testament to the researchers' deep understanding of polymer chemistry. Section 5, Gamma Irradiation, the driving force of synthesis. The creation of this remarkable tri-copolymer relies on a fascinating process, gamma irradiation. This method, often associated with powerful energy sources, is harnessed here with precision and control. Imagine a beam of energy, invisible to the naked eye, interacting with individual molecules, causing them to link and rearrange themselves in a specific order. Gamma irradiation acts as that invisible architect, guiding the formation of the tri-copolymer's intricate structure. This method, while powerful, is carefully controlled to ensure the creation of a material with the desired properties for waste ink capture and removal. Section 6. A closer look, analytical techniques employed. To confirm the efficacy of their creation, the research team employs a suite of advanced analytical techniques. These methods are crucial in ensuring that every aspect of the tri-copolymer is thoroughly understood and optimized for its intended applications. FAFTIR, TGA, DSC, and SEAM, each like a powerful lens, allow the researchers to peer into the very structure and behavior of the tri-copolymer. These instruments provide a comprehensive analysis, from molecular composition to thermal properties and surface morphology. FTR, or Fourier Transform Infrared Spectroscopy, acts as a molecular fingerprint scanner, revealing the unique chemical bonds within the tri-copolymer. This technique helps identify specific functional groups and monitor chemical changes during synthesis. TGA, or thermogravimetric analysis, measures the tri-copolymer's response to heat, providing insights into its stability and degradation patterns. By analyzing weight changes under controlled temperature conditions, researchers can predict the material's performance in various environments. DSC, or differential scanning calorimetry, delves into the tri-copolymer's thermal transitions, such as melting and glass transition temperatures, further characterizing its physical properties. This information is vital for understanding how the material behaves under different thermal conditions. Finally, SEM, or scanning electron microscopy, provides high-resolution images of the tri-copolymer's surface, revealing its morphology and porosity. These detailed images help researchers understand the material's structural integrity and potential applications in various fields.
Section 7. Dr. Ibrahim's Insights. Pioneering Polymer Chemistry. Dr. Saber Ibrahim, a leading expert in polymer chemistry, spearheaded the synthesis of the tri-copolymer. His deep understanding of molecular interactions and his innovative approach to polymer design were instrumental in creating this remarkable material. Our goal, Dr. Ibrahim explains, was to develop a material that could effectively target and remove the harmful components of waste ink, and this tri-copolymer does just that.
His vision and expertise laid the foundation for this groundbreaking research, pushing the boundaries of polymer science for a sustainable future. Section 8, Dr. Fahmy's expertise navigating the analytical maze. Dr. Hager Fahmy, an expert in analytical chemistry, played a crucial role in verifying the effectiveness of the tri-copolymer. Her meticulous analysis, utilizing a range of sophisticated techniques, provided irrefutable evidence of the material's ability to capture and remove waste ink pollutants.
The results were remarkable. The data clearly demonstrated the tri-copolymer's high affinity for the target pollutants.
Her expertise in interpreting complex analytical data ensured the accuracy and reliability of the research findings, confirming the tri-copolymer's effectiveness in real-world applications. Section 9. Dr. Lotfy's contribution. Optimizing for real-world application, Dr. Salah Lotfy, a specialist in radiation technology, focused on optimizing the gamma irradiation process. His research determined the ideal radiation dose for synthesizing the tri-copolymer, ensuring its effectiveness while minimizing energy consumption.
Finding the optimal dose was crucial. It allowed us to maximize the tri-copolymer's performance while making the process more efficient and sustainable.
His work bridged the gap between laboratory synthesis and practical application, paving the way for the tri-copolymer's use in large-scale waste ink treatment. Section 10. A sustainable future. The promise of green printing. The implications of this research extend far beyond the laboratory. The tri-copolymer, with its ability to effectively remove pollutants from waste ink, holds the potential to revolutionize the printing industry. Imagine a future where printing, a process essential to our daily lives, no longer carries the burden of environmental pollution. This research brings us closer to that vision, a future of green printing, where sustainability and environmental responsibility are paramount. The tri-copolymer's ability to transform waste ink into a reusable resource opens up exciting possibilities for a circular economy within the printing industry. Section 11. Conclusion. Towards a cleaner, greener tomorrow. The collaborative efforts of Dr. Ibrahim, Dr. Fahmy, and Dr. Lotfy represent a beacon of hope in the fight against industrial pollution. Their innovative use of gamma irradiation to synthesize the PEI-PGMA-PEGDA tri-copolymer provides a sustainable and effective solution for waste ink management in the flexographic printing industry. As we strive towards a cleaner, greener future, such groundbreaking research serves as a testament to the power of human ingenuity and collaboration in tackling the world's most pressing environmental challenges. Their work inspires us all to seek innovative solutions and to work together to preserve the health of our planet for generations to come. Hey there, science fans. Today we're diving into a topic that's often overlooked but incredibly important. We all know how important printing is. It's a cornerstone of how we share information and communicate ideas. It's how we read books, magazines, and even this very essay. But have you ever thought about what happens after we finish reading? What happens to all that paper and ink after we're done with it? The journey doesn't end when we put it down. That's where waste management comes in. It's a crucial process that ensures our waste is handled properly. Printing creates a lot of waste, and it's important to deal with it responsibly. This involves recycling and proper disposal methods. If we don't, it can harm the environment and even our health. Improper disposal can lead to soil and water contamination. Let's learn more. The printing industry uses tons of paper, ink, and other materials every year. Much of this ends up in landfills, taking up space and potentially leaching harmful chemicals into the ground. This is a growing concern. Much of this ends up in landfills, taking up space and potentially leaching harmful chemicals into the ground. This is a growing concern. Some printing waste is incinerated, which can release pollutants into the air. This method also has its drawbacks. Neither of these options is ideal. Both landfilling and incineration have significant environmental impacts. That's why we need to find smarter ways to manage printing waste. Innovative technologies and better practices can make a big difference. Printing inks contain a variety of chemicals, some of which can be harmful to the environment and our health. These chemicals are used to achieve the vibrant colors and durability we expect from printed materials, but they come with significant risks. These chemicals can include heavy metals, volatile organic compounds, and pigments. Heavy metals like lead and cadmium are particularly concerning because they can accumulate in living organisms over time, leading to toxic effects. When printing waste isn't disposed of properly, these chemicals can contaminate soil, and water sources, this contamination can persist for years, affecting ecosystems and human communities alike. This can harm plants and animals, disrupting food chains and leading to loss of biodiversity. Aquatic life is especially vulnerable to these pollutants, and it can even make its way into our food and drinking water. Contaminated water sources can affect entire communities, leading to long-term health issues. Exposure to certain printing chemicals can also pose risks to human health. Workers in the printing industry are particularly at risk due to prolonged exposure. Volatile organic compounds, for example, can irritate the eyes, nose, and throat. Long-term exposure can lead to chronic respiratory problems. Some printing chemicals have been linked to more serious health problems like respiratory issues, skin allergies, and even cancer. The risk is not limited to workers. Consumers can also be affected through contact with printed materials. It's clear that we need to find safer ways to handle printing waste to protect both the environment and ourselves. Implementing stricter regulations and developing eco-friendly alternatives are crucial steps in mitigating these risks. Now let's talk about a really cool and innovative solution for managing printing waste: gamma irradiation. This cutting-edge technology is making waves in the scientific community. Gamma irradiation is a fascinating process that uses high-energy gamma rays to modify materials at a molecular level. It's a game changer in material science. It's almost like giving these materials a superpower, enabling them to perform functions they couldn't before. One of the most amazing things gamma irradiation can do is help create special materials called tri-copolymers. These tri-copolymers are incredibly useful and can be employed to clean up printing waste efficiently. Gamma rays are a type of electromagnetic radiation, just like light and X-rays. However, they possess unique properties that set them apart. But gamma rays are much more energetic, packing a powerful punch that can be harnessed for various applications. This immense energy can be harnessed to break chemical bonds and create new ones, transforming the chemical structures of materials. When certain chemicals are exposed to gamma irradiation, they can link together to form long chains called polymers. This process is crucial for creating new materials. Tri-copolymers are a special type of polymer made up of 3 different building blocks, or monomers. These unique structures give them properties that are ideal for tackling printing waste. To create tri-copolymers for managing printing waste, scientists start with carefully selected chemicals. These chemicals act as the building blocks, or monomers, for the tri-copolymer. The monomers are dissolved in a special solution and then exposed to gamma irradiation. The gamma rays provide the energy needed for the monomers to link together and form long chains. The specific monomers used depend on the properties desired in the final tri-copolymer. For example, some monomers are chosen for their ability to absorb specific printing ink components. Others might be chosen for their strength, flexibility, or ability to degrade safely in the environment. By carefully selecting the monomers and controlling the irradiation process, scientists can create tri-copolymers tailor-made for specific waste management applications. Section 5. Tri-copolymers, tiny helpers with big potential. Tri-copolymers are like tiny sponges that can selectively soak up certain substances. This makes them incredibly useful for cleaning up waste. In the case of printing waste, tri-copolymers can be designed to absorb excess ink, solvents, and other unwanted chemicals. This helps prevent these substances from contaminating the environment and causing harm. Imagine a tri-copolymer as a microscopic net with holes just the right size to trap ink molecules. These nets can be added to wastewater treatment systems at printing facilities. As the wastewater flows through, the tri-copolymers capture and hold onto the ink, preventing it from polluting waterways. This helps protect aquatic life and ensures cleaner water for everyone. Section 6. Soaking up the problem: flexographic waste ink sorption. Flexographic printing is a popular method used for printing on various surfaces, including packaging materials. However, it often generates a significant amount of waste ink. This is where tri-copolymers come in handy. Scientists have conducted experiments to see how well tri-copolymers can remove waste ink from flexographic printing processes. In these experiments, tri-copolymers were added to samples of wastewater containing flexographic ink. The results were impressive. The tri-copolymers were able to absorb a significant amount of the ink, effectively removing it from the water. This demonstrates the potential of tri-copolymers as a sustainable solution for managing flexographic printing waste. Section 7. Saving money, saving the planet. Using tri-copolymers to manage printing waste isn't just good for the environment, it's also good for business. By reducing waste and improving efficiency, printing companies can save money in the long run. They can also reduce their environmental footprint and enhance their reputation as responsible corporate citizens. When printing companies invest in sustainable waste management practices, they're making a smart investment in their future. They can reduce their reliance on landfills and incineration, which can be costly. They can also potentially explore new markets for recycled materials and eco-friendly printing solutions. Section 8. A sustainable future for printing. The printing industry plays a vital role in our world, and it's important that it operates in a way that protects our planet. By embracing innovative solutions like gamma irradiation and tri-copolymers, the printing industry can move towards a more sustainable future. This will benefit not only the industry itself, but also the environment and all of us who rely on a healthy planet. Imagine a future where printing waste is no longer a problem. Tri-copolymers and other advanced materials could be used to capture and recycle valuable resources, reducing the need for virgin materials. Printing processes could be optimized to minimize waste and energy consumption, further reducing the industry's environmental impact. Section 9. The science behind the solution. The development of tri-copolymers for waste management is a testament to the power of science and innovation. By understanding the properties of different materials and the principles of chemistry, scientists have been able to create a solution that addresses a pressing environmental challenge. The use of gamma irradiation to synthesize tri-copolymers is a prime example of how cutting-edge technology can be harnessed for the greater good. This process allows for the precise control of the tri-copolymers' properties, ensuring its effectiveness in capturing and removing specific pollutants from printing waste. Section 10. Challenges and opportunities. While the use of tri-copolymers for printing waste management holds great promise, there are still challenges to overcome. One challenge is the cost of producing tri-copolymers on a large scale. Further research and development are needed to make this technology more commercially viable. Another challenge is ensuring that the tri-copolymers themselves are environmentally benign and don't pose any risks to human health or ecosystems. Life cycle assessments should be conducted to evaluate the overall environmental impact of these materials from production to disposal. Section 11. A call to action embracing sustainable printing. It's time for the printing industry to embrace sustainable practices and invest in innovative solutions like gamma irradiation and tri-copolymers. By working together, we can reduce the environmental impact of printing and create a cleaner, healthier future for everyone. Consumers can also play a role by supporting printing companies that prioritize sustainability, choose products made with recycled materials, and look for certifications that indicate environmentally responsible manufacturing practices. Together, we can make a difference.
The printing industry brings vibrant colors to our world, filling our lives with vivid images and important information. But it also produces a lot of waste, which often goes unnoticed by the end users. Leftover inks, especially, pose a big problem. These containers accumulate quickly, creating a significant environmental challenge. These inks contain pigments and chemicals that can harm the environment if not properly treated. Improper disposal can lead to soil and water contamination. We need innovative solutions to clean up this colorful mess. Researchers are working tirelessly to find effective methods to manage and reduce ink waste. One promising approach uses special polymers to remove ink from wastewater. These polymers are designed to target and capture ink particles. These polymers act like tiny sponges, soaking up ink molecules from the water. This innovative method shows great potential in reducing ink pollution. This process helps to decontaminate the wastewater, making it safe for disposal or reuse. It ensures that harmful chemicals do not make their way back into our ecosystems. But how do we know if these polymers are really working? Continuous research and testing are essential to measure their effectiveness. That's where some high-tech tools come in handy. Advanced monitoring devices help scientists track the performance of these polymers, ensuring they meet environmental safety standards. One way to track the effectiveness of ink removal is by looking at the color of the water. UV-vis spectrophotometry is a technique that helps us do just that. It works by shining a beam of light through the water sample. The instrument then measures how much of the light passes through at different wavelengths. Different colors absorb light differently. By analyzing the pattern of absorption, we can determine the concentration of specific dyes or pigments in the water. By comparing the color intensity before and after treatment, we can see how much ink the polymer has removed. Knowing how much ink is removed is important, but we also want to know how efficient the process is. Efficiency is key to understanding the overall effectiveness of the treatment. Adsorption efficiency is a measure of how well the polymer can capture and hold on to the ink molecules. This metric is essential for evaluating the performance of the polymer. It tells us what percentage of the initial ink concentration is removed from the water. This percentage is a direct indicator of the treatment's success. The formula for adsorption efficiency is adsorption efficiency percent equals CI minus CE divided by CI times 100. This formula helps us quantify the efficiency in a precise manner, where C is the initial concentration of ink, which is the amount of ink present in the water before treatment begins, and C is the equilibrium concentration of ink after treatment. This is the amount of ink left in the water after the polymer has done its job. A high adsorption efficiency means that the polymer is doing a great job of removing ink from the water. This indicates that the treatment process is highly effective. This information is crucial for designing effective and sustainable ink waste treatment systems. By understanding adsorption efficiency, we can develop better methods to treat ink waste, ensuring cleaner water and a healthier environment. To understand why these polymers are so good at capturing ink, we need to look at their chemical structure. Fourier transform infrared spectroscopy, or FTIR, allows us to do just that. FTIR spectroscopy works by shining infrared light through a sample and measuring how much of that light is absorbed. Different chemical bonds absorb infrared light at specific frequencies. By analyzing the pattern of absorption, we can identify the types of chemical bonds present in a molecule. In the case of our ink-absorbing polymers, FTIR can tell us about the functional groups responsible for binding to ink molecules. Section 5. A closer look, scanning electron microscopy and polymer morphology. In this section, we delve into the fascinating world of polymers and how advanced microscopy techniques help us understand their intricate details. FTIR, or Fourier transform infrared spectroscopy, gives us valuable information about the chemical makeup of the polymers. It helps us identify the different chemical bonds and functional groups present in the material. But what about their physical structure? Understanding the physical arrangement of polymer chains is crucial for many applications. Scanning electron microscopy, or SEM, allows us to visualize the surface of materials at a very small scale. This technique provides high-resolution images that reveal the fine details of the polymer surface. SEM works by scanning a focused beam of electrons over the surface of a sample. The electron beam interacts with the sample, producing various signals that are detected and used to form an image. The electrons interact with the atoms in the sample, producing various signals, such as secondary electrons, backscattered electrons, and X-rays. These signals provide different types of information about the surface. SEM can reveal the size, shape, and arrangement of the polymer particles. This information is crucial for understanding the material's properties and behavior. This information is important for understanding how the polymers interact with ink molecules. By studying these interactions, we can improve the performance of polymer-based inks and coatings in various applications, from printing to packaging. Section 6. Testing the heat, thermogravimetric analysis, and polymer stability. Treating ink waste often involves high temperatures. We need to make sure our polymers can withstand the heat without breaking down. Thermogravimetric analysis, or TGA, helps us determine the thermal stability of materials. TGA works by measuring the weight of a sample as it is heated up in a controlled environment. If the material decomposes upon heating, it will lose weight. By analyzing the weight loss as a function of temperature, we can determine the temperature range over which the polymer remains stable. This information is crucial for optimizing the ink treatment process. Section 7. Thermal insights. Differential scanning calorimetry and polymer behavior. In addition to stability, we also want to know how the polymers behave at different temperatures. Differential scanning calorimetry, or DSC, provides insights into the thermal transitions of materials. DSC measures the amount of heat required to maintain a constant heating rate between a sample and a reference. When a material undergoes a phase transition, such as melting or crystallization, it either absorbs or releases heat. DSC detects these changes in heat flow, providing valuable information about the melting temperature, glass transition temperature, and other thermal properties of the polymers. Section 8. A sustainable solution. The promise of PEI-PGMA-PEGDA, ternary polymers. One specific type of polymer showing great promise for ink waste treatment is the PEI-PGMA-PEGDA ternary polymer. This complex-sounding name represents a combination of 3 different polymers, each with its own unique properties. This ternary blend exhibits high adsorption efficiency for a wide range of inks. It can remove over 90% of certain dyes from wastewater. What makes this ternary polymer so effective? The answer lies in its structure and chemical composition. The combination of 3 different polymers creates a material with a large surface area and abundant binding sites for ink molecules. Section 9. Looking ahead. The future of sustainable ink waste treatment. The development of effective ink waste treatment methods is crucial for a sustainable printing industry. PEI-PGMA-PEGDA ternary polymers represent a significant step forward in this direction. They offer a combination of high adsorption efficiency, thermal stability, and cost-effectiveness. Further research and development in this area will focus on optimizing the polymer synthesis process, exploring new polymer combinations, and scaling up the technology for industrial applications. Section 10. Conclusion. Embracing innovation for a greener printing industry. As we strive for a more sustainable future, it is essential to address the environmental challenges posed by industrial processes like printing. Ink waste treatment is a critical aspect of this endeavor. Innovative solutions like ternary polymers, coupled with advanced analytical techniques, offer hope for a cleaner and greener printing industry. By embracing these advancements, we can continue to enjoy the vibrant colors of printed materials while minimizing their impact on our planet.
We use a lot of packaged goods in our daily lives, from food items to household products. These goods need to be printed on to provide essential information and branding. Flexographic printing is a popular method that companies use to print on various types of packaging materials. Think about the plastic wrap around your favorite snack or the labels on your beverages. That's flexography in action. This printing technique uses a significant amount of ink to achieve high-quality prints. However, the process generates a considerable amount of ink waste, which poses a challenge. This ink waste can be detrimental to the environment if not managed properly. Therefore, it is crucial to find effective ways to treat and reduce this ink waste. Scientists around the world are working diligently to discover and implement solutions. They are developing innovative methods to treat and minimize the impact of ink waste. One promising method is called sorption-based treatment. Let's delve into how this technique works and its potential benefits. Imagine a sponge. When you put a sponge in water, it absorbs the water. Sorption-based treatment is similar. It uses special materials to absorb the ink waste. These materials are like super sponges. They are designed to attract and hold on to the ink molecules. This process helps to remove the ink waste from the environment. But how do we make these super sponges? This is where gamma irradiation comes in. Gamma irradiation is a powerful tool. It uses gamma rays to change the properties of materials. Think of it as giving these materials superpowers. Scientists use gamma irradiation to create the super sponges. These sponges can then absorb the ink waste. This is a very effective way to treat the waste. This innovative method was developed by a team of Egyptian researchers. Let's meet these science heroes. Section 4, recognizing the pioneers, Egyptian researchers leading the way. Dr. Saber Ibrahim, Dr. Hager Fahmy, and Dr. Salah Lotfy are the brilliant minds behind this groundbreaking research. They worked tirelessly, dedicating countless hours to find a sustainable solution to this pressing environmental challenge. Their dedication and expertise led to the development of this innovative treatment method, which has the potential to revolutionize the field. Their work is a testament to the power of scientific inquiry and the relentless pursuit of knowledge. This research was supported by leading scientific institutions in Egypt, showcasing the country's commitment to advancing science. Let's delve deeper into their remarkable contributions and understand the impact of their work on the global stage. Section 5, Collaborative Efforts, NCRRT and Nanomaterials Investigation Laboratory. The National Center for Radiation Research and Technology, or NCRRT, played a crucial role in this research. They provided the gamma irradiation facilities. These facilities were essential for creating the super sponges. The Nanomaterials Investigation Laboratory also contributed to this project. They helped to analyze the materials and optimize the treatment process. This collaboration between researchers and institutions is commendable. It highlights the importance of teamwork in scientific advancements. Section 6, Conclusion, Appreciating Scientific Endeavors. In this section, we reflect on the incredible journey of scientific discovery and innovation. The development of this innovative ink waste treatment method is a remarkable achievement. It stands as a testament to the relentless pursuit of solutions to pressing environmental issues. It demonstrates the power of science to address environmental challenges. Through rigorous research and experimentation, scientists have shown that even the most complex problems can be tackled. Let us take a moment to appreciate the hard work and dedication of Dr. Ibrahim, Dr. Fahmy, Dr. Lotfy, and the teams at NCRRT and the Nanomaterials Investigation Laboratory. Their tireless efforts and unwavering commitment have paved the way for groundbreaking advancements. Their efforts bring us closer to a cleaner and more sustainable future. By developing innovative solutions, they are helping to create a world where environmental sustainability is within reach. Remember, science is a collaborative effort. It thrives on the collective intelligence and cooperation of diverse minds working together towards a common goal. It thrives on curiosity, innovation, and the pursuit of knowledge. The drive to explore the unknown and push the boundaries of what is possible fuels scientific progress. Let us continue to support and encourage scientific endeavors for a better tomorrow. By fostering a culture of curiosity and innovation, we can ensure that future generations inherit a world brimming with possibilities and solutions.